We are going to talk about database concurrent transactions and isolation levels in this video. When we have two or more transactions running at the same time, we call them as concurrent transactions. This is very common because more than one application or users might be connected to a database and they might be executing transactions of their own. But when we have concurrent transactions like these, database must define how those transactions will be handled. We are going to look at some of the common problems that we will have when we are running concurrent transactions and the solution for those problems in the form of transaction isolation levels. But let's go back to the beginning and understand what concurrency means. People often confuse concurrency with parallelism, but they are two different things. One of the way I think to differentiate between concurrency and parallelism is that for concurrency, imagine that you have a single computer and two or more people are using the same computer by taking a turn. And for parallelism, imagine that you have two different computers and two different people are using them, one for each. So when we are talking about concurrent transactions, we are talking about two different transactions running at the same time, but not necessarily they are running in parallel. Concurrency can be implemented using time sharing. In that case, think that you have a single computer and in that single computer we are trying to run two different transactions and we'll be running one transaction for set amount of time, then we'll be switching back to other transaction and run the transaction for another set of time, then we'll be coming back to the previous transaction. So this is how concurrent transaction will be implemented in time sharing. Concurrent transaction can also be implemented using parallelism if the underlying hardware supports it. For example, imagine that you have multiple cores in your computer and if you have multiple transactions, each transaction can be executed in parallel in their own CPU core. But in general, concurrent transactions are implemented using time sharing because ultimately they need to be run one after the other to avoid some of the data consistency issues. Okay, now we understand what is concurrent transaction. Let's look at some of the common problems that might arise when we are running transactions concurrently. The first one is called a dirty read. Imagine that you have two different transactions, T1 and T2. When these two transactions are running concurrently, let's say transaction 1 has made some changes in one of the table and the change is not committed yet. But transaction 2 is started around the same time, and if this transaction 2 can see the uncommitted changes of transaction 1, then the data read by transaction 2 is called dirty read because it has read the data or it has seen the data that is not yet committed by transaction 1. So this is dirty read. This is generally not good because this transaction could roll back as well. There is no guarantee that T1 is going to commit. So if T2 is reading and using this uncommitted data, then if T1 rolls back, then the operation done by T2 could be invalid. So this is why dirty read is one of the problem. And the second problem is called non-repeatable read. Let's go back to the same problem where we have two different transactions running concurrently, T1 and T2. Now transaction 1 has started and transaction 2 also started around the same time. Within transaction 1, we made some changes and we changed some of the records. And within T2, we read the same record just before T1 updated them. And then within the transaction 2, we're reading the same a little bit later. When we read the data a little bit later, we notice that the data has changed. So this is non-repeatable read. Because when we read the same data more than once within the same transaction, we see different results. If we have read the data within T2 just before T1 has updated them, then we would have seen one version. And if we have read the data just after T1 has updated them, then we will see different data. So we will not be able to reliably read the same data repeatably. So that is what non-repeatable read is. This is again a problem because if we have read the data and done some business logic based on the data, but later we realize that the data has changed, then the business operation that we have done might not be valid and we might need to undo that. So again, this is not a good scenario to be in. The third one is called phantom read. Phantom read is very similar to non-repeatable read, but the difference is rather than changes to the existing record, when T2 reads data, it might see more or less rows because T1 may have added or removed some of the rows that T2 is trying to read. So let's imagine first T2 is reading some records from the database. It has found that 10 matching records. Then it is doing something with that. While T2 is still in progress, T1 also deletes some of the records. And some of the records deleted by T1 includes some of the records read by T2. Let's say, for example, T1 has deleted 5 of the records read by T2. Now, if T2 runs the same query within the same transaction, just after T1 has committed its changes, T2 will only see 5 records this time. And it can be the other way around as well. If T1 has inserted some rows and if those rows are picked up by the query run by T2, then the first time when T2 runs the query, it might see 10 records. And the second time, just after T1 completes, if T2 runs the same query, it might see some additional rows. So this is what we refer to as phantom read. Okay, so the number of rows increasing or decreasing within the same transaction when we run the same query. That is called phantom read. So these are some of the problems that we will have with concurrent transactions. To solve these problems, most databases define different isolation levels. So what is isolation levels? Isolation level is nothing but a way to balance the competing needs. What are those competing needs? We have consistency versus concurrency. So if we have any of these problems, then we can say that we don't have consistency, because when we are doing dirty read, we have read some data and that data may not exist a little bit later, right? So these are different inconsistency issues. Now the database must balance between consistency and concurrency. We still want to allow concurrency because there is no point in allowing only one transaction at a time, because that will be severely limiting. But at the same time, we don't want this inconsistency issue. But these are two competing requirements. We cannot have both of them solved at the same time. We need to make some compromises. If you are going for high concurrency, we might allow some inconsistency. Whereas if you are going for high consistency, then we might compromise on the concurrency. So this is where isolation levels comes into picture. These are some of the common isolation levels, and these isolation levels provide a different level of consistency and concurrency. So the first one is called read uncommitted. Read uncommitted allows uncommitted changes from other transaction. So if I go back to the previous example, if we have two transactions T1 and T2, if these two have started around the same time and T1 has done some changes and those changes are not committed yet, if you are using read uncommitted transaction isolation level, then T2, which started around the same time as T1, will be able to see uncommitted changes by T1. So this is what read uncommitted means. But if you are using read uncommitted isolation level, then we'll have all three of these problems. We'll have a dirty read, non-repeatable read, and phantom read. All three problems will be there. None of these problems will be solved, but it will allow very high concurrency. The second one is called read committed. This is the most common and default isolation level in most of the databases. What read committed means, if we have two transactions T1 and T2 started around the same time, then one transaction can see other transactions committed changes. They'll not be able to see uncommitted changes. So if T1 has made some changes and it has committed those changes, then only those changes can be seen by T2. If T1 has some uncommitted changes, then those changes cannot be seen by T2. So this is what read committed means. And like I said, this is the most common isolation level in most of the databases. With read committed, we are solving only dirty read problem. Non-repeatable read and phantom read problems are still there with read committed isolation level. The next one is called repeatable read. In repeatable read, if you take the same transactions T1 and T2, if T2 is running some query within a transaction, then it doesn't matter how many times and in how many places that particular query is run, it will get same result back. Usually this is implemented using some sort of locking mechanism where if T2 has read some data, for example, and if some other transaction is trying to change the data, for example, T1 is trying to change the data that T2 has already read, then T1 will not be allowed to change the data until T2 has completed. So this way, if T2 runs the same query within the same transaction in different places, it will be guaranteed to see same data. It's simply because other transactions are not allowed to change this data until T2 is completed. So this is what repeatable read, and this repeatable read solves both dirty read and non-repeatable read problems. So read committed solves dirty read, and repeatable read solves both dirty read and non-repeatable read. The next one is called serializable. Serializable provides very low concurrency but high consistency. So this is achieved by sort of allowing only one transaction at a time to run. So that is what serializable means. We are serializing concurrent transactions to run one at a time. This is again implemented using some sort of locking mechanism, where if one transaction has started and if another transaction is trying to use the same set of data, then the second transaction will be blocked until the first transaction has completed. So this solves all three problems. This solves dirty read, non-repeatable read, and it also solves phantom read. But the compromise here is that we have achieved high consistency, but the concurrency is very low. The last one is called snapshot. Snapshot is very similar to serializable, but the difference is it allows you to run multiple transactions concurrently without using any sort of logs by creating a snapshot of the data for each of the transactions. So let's say, for example, transaction 1 and 2 are starting around the same time, then both transactions will get their own snapshot of the database, and each of these transactions will use their own snapshot without any locking. But later, when we are trying to persist those changes, as in we are trying to commit those changes, then if there are any conflicts between those two transactions, one of the transaction will be aborted. So this allows sort of little bit better concurrency level than serializable, but we are at the risk of aborting one of the transaction if there are any conflicts. As in, if both T1 and T2 are trying to update the same record with different values, for example, then they are able to do so because they have their own snapshot of the database. But when they try to commit the changes to the main database, one of the transaction has to be aborted because we don't know which changes must be persisted, whether the T1 changes or T2 changes. So one of the transaction has to be aborted to keep the database in a consistent state. That is the problem with snapshot. And the other problem with snapshot isolation level is that because we are going to create snapshot for each transaction, we might need to use a lot of computer memory to maintain for the duration of the transaction. So this again solves all three of the problems, but it comes with its own new problems, which is high memory usage, and we are at the risk of aborting some of the transaction. Okay. So we looked at what is concurrency and parallelism. We looked at some of the problems with concurrent transactions. Then we looked at different isolation levels, and we also looked at what problems are solved by each of these isolation levels. Hope this is useful. Thank you.